right. Um, Hello, class. Mr. P here. I am going to take tomorrow off, I think, because I'm realizing that I have a lot of November 1st letter of recommendation deadlines. I have a lot of letters to write by November 1st, and I didn't quite realize how many there were. So I'm going to take tomorrow off and write some letters of recommendation. So I'm recording my lesson tonight, and you guys are going to work on Momentum Quiz 2. Okay, you will take attendance, do the attendance form like you normally would. Okay, because I'm still going to submit attendance. I'm literally going to be in the same place I am every day. When I teach you guys, I'm just not going to be teaching you guys. I'm going to be writing letters of recommendation. Okay, so I will have time to submit attendance. So submit the attendance form as you normally would. If you don't submit the attendance form, I have no way of verifying that you were present. So you'll be absent. Okay. To make up for the office hours, I'll do, maybe a double office hours on Tuesday, or maybe a 1.5 office hours on Tuesday. I don't know. All right, so I'm going to go ahead and get started. So this is our second momentum lesson, okay? And so the first thing I wanted to talk about is energy dissipated / released in collisions. Okay. So let's do an example problem. It's easier explained with an example. Okay. Let's suppose we have a 4 kilogram object that is traveling this way at 10 meters per second. And then we have a 1 kilogram object that is traveling this way at 3 meters per second. Okay? They collide and they stick together. Okay? And so let's go ahead and get the final velocity first, and then we'll get to sort of the main focus of this problem. So really quickly, doing initial this is a collision problem. It's a completely inelastic collision, so they have the same velocity afterwards. P initial equals P final. Initially, we have a 4 kilogram mass going to the right at 10 meters per second, so that's 4 times 10. And then we have a 1 kilogram mass going to the left at 3 meters per second, so that's plus 1 times negative 3. All right, so that's an expression for the initial momentum. The final momentum is going to be 5 VF. Okay, so we have 40 minus 3, that is 37, equals 5 V final. Okay, so dividing both sides by 5 gives 7.4 meters per second is V final. Okay, so that's what we did last time. Okay. So now what I would like to do is I would like to look at the energy. What is the total kinetic energy of the system before and the total kinetic energy afterwards? Okay. So um, initially we have a kinetic energy of 1/2 mv squared, but we have two 1/2 mv squareds because we have two masses. Okay. So we have 1/2 times 4 times 10 squared. And then we have 1/2 times 1 times 3 squared. All right? Actually, this should be -3 squared, but because we square it, the negative goes away. All right? So that's an important point. Even though this is going to the left, it is still a positive kinetic energy. Okay? If you're going to the left, you have a negative momentum, but if you're going to the left, you still have a positive kinetic energy. So working this out, we have 400 divided by 2, 200, and then 9 divided by 2 is 4.5. For an initial kinetic energy of 204.5 joules. Okay? For the final kinetic energy, these two masses are acting as one object. So we have 1/2 m, which is 5, times v squared, so 7.4 quantity squared. All right. And so working that out, so this is the final kinetic energy. I'm using the final velocity of the pair. I'm using the mass of the pair. And that's 136.9 joules. Okay? So if we subtract these two, we can figure out, we notice that the initial kinetic energy is not equal to the final kinetic energy. Okay, so that means kinetic energy was lost. The initial kinetic energy is greater than the final. So how much was lost? It would be 204.5 minus 136.9 equals 67.6 joules was, I'm going to put quotes around it, lost. So where did that energy go? As you know, energy is conserved. It cannot be created or destroyed, okay? But it can be transformed. And so what happens in a completely inelastic collision is that you have perhaps energy is turned into heat, okay? You could have energy turned into kinetic energy turned into the energy of sound waves, which we'll learn about later. Sound waves carry energy. You could have that the collision deforms these two masses so that they no longer have the same shape, and so that takes energy to do. So that the energy isn't disappearing, it's just becoming something other than kinetic energy, most likely heat. Okay? So, you know, you could say 67.6 joules became heat. All right? I'm not going to actually work out the math because it's analogous, but I'm still going to call it another example. You might recall we did this recoil velocity problem where we had the astronaut with the rifle. Okay, astronaut fires the rifle and the bullet goes this way. The astronaut goes this way. Okay, so if we think about it, bullet, rifle, astronaut all start out at rest. Okay, so the initial kinetic energy is 0 because kinetic energy is the energy of motion. So if there's no motion, then there's not going to be any kinetic energy. Okay. However, if we look at it, we have motion after this rifle bullet is fired. And so afterwards, we have a kinetic energy that is greater than 0. It's not 0 anymore. Okay? So what happened here? Well, we had kinetic energy being created. So that means that that there's a kinetic energy gain. The final kinetic energy is greater than the initial kinetic energy. Where did that energy come from? It came from chemical potential energy of the powder or whatever was used to fire the bullet. Okay? So basically we had chemical potential energy became kinetic energy. Okay? The important thing to understand, though, is that even though these energy transformations are taking place, momentum is still conserved. Okay? Momentum is king when it comes to collision type problems. All right? So that's kind of the first part of the lesson. The second part, I want to talk about what I like to call the sneaky form of Newton's second law. Okay? The sneaky form of Newton's second law. So the way it works is you have I'm going to start off with an expression for the change in momentum over the change in time. Okay? So the change in momentum over change in time. Well, momentum is mass times velocity. Okay? And if we have a particle, its mass is not changing. So the only thing that's changing is the velocity. So we can actually factor out the mass here. Okay? So we have m times change in velocity over change in time. Change in velocity over change in time is acceleration. Okay? And mass times acceleration is net force. So the sneaky form of Newton's second law is that the net force is equal to the rate of change of momentum. Okay? That's called the sneaky form of Newton's second law. So that has a lot of applications, which I'm going to do a couple of examples on right now. Okay? All right. So the first example I want to do is what I like to call a force of impact problem. So let's suppose I have a ball, and the ball has a mass of, let's say, 2 kilograms. So it's a pretty heavy ball. You probably wouldn't be throwing this ball very quickly, but it is what it is. The ball is headed towards the wall, okay, and it's headed towards the wall at a speed of 10 meters per second. The ball hits the wall, and then it bounces back off the wall with a speed of 8 meters per second. So it loses a little bit of speed. Now, here's the thing. You record this collision using an ultra high speed camera. Okay? Has anyone ever seen those ultra high speed cameras where it's so high speed that you can actually see the ball begin to make contact with the wall, deform and get compressed, and then snap back into shape and head back in the opposite direction. Okay, there are cameras that can do that. I think there might be a YouTube channel that does that. It's called like Slow-Mo Guys or something like that. And so because you have this high-speed camera, you know that the ball was in contact with the wall for, let's say, 0.0026 seconds. Okay? So we can actually use this. We can actually use this to determine what was the force the ball exerts on the wall. Or what is the force that the wall exerts on the ball? My bad. Okay, so if we look at this, the original momentum is 2 times 10 equals 20 kilogram meters per second. Okay, the final momentum, it's important to realize that the final speed is 8 meters per second, not the final velocity, but the final speed. So the velocity is actually going to the left, so it's negative. So the final momentum is 2 times negative 8, which is negative 16 kilogram meters per second. So that means that the change in momentum is final momentum minus initial momentum. Okay. Equals negative 16 minus 20 equals negative 36 kilogram meters per second. So that's the change in momentum. All right. Net force is change in momentum divided by change in time. So that's going to be negative 36 divided by 0.0026, which is a net force of, this is kind of getting crowded. I'm rounding here, but the net force is about negative 13,800 newtons. Okay? So quite a large force. But it's a very brief force. So you can use the sneaky form of Newton's second law to infer the force of impact. Okay, so I would call this a force of impact problem. We saw how much force is it. So for example, if you punch someone, you're causing a change in momentum of the person's head over a certain amount of time. So if you did that, you could figure out what was the force that your fist exerted on the person's face. Okay. One of the things boxers do, if they are, if a boxer is getting punched, what they're trained to do is to move their head back. Okay, when they get punched. Now, by doing that, by moving their head back with the punch, they're increasing the amount of time that the fist is in contact with the face. Okay, so you can see if we make the amount of time bigger, we're making the denominator larger, which reduces the force. Okay, So it's less painful if you move your head back with the punch. Okay. I would like to define something called the impulse, which is denoted by J. And there are two ways that in the IB class impulse is calculated. So the first way is if you have a constant force. Okay, if you have a constant force, then the impulse is going to be the size of that force times the amount of time that that force acts for. Okay, so that is one way that you can calculate impulse. The second way is if you have a non-constant force. And if you have a non-constant force, then you have to say, well, gee, how is this force not constant? Okay. And so to say how the force is not constant, you have a force versus time graph. It looks like this. Okay. And the area under the curve of that graph is going to be impulse. All right? So you might encounter either of these. The units of impulse are force times time. So that is newtons times seconds. So Newton seconds. N times S. All right. One thing I want to do is I want to talk about how impulse is not the same thing as work. Okay? Impulse is not the same thing as work. Work is the area under the curve of a force versus position graph. Okay? Impulse is the area under the curve of a force time graph. All right? Work tells you the change in energy. Initial energy plus the work done equals the final energy. Okay? Impulse tells you the change in momentum. P initial plus the impulse equals P final. Okay, so there basically impulse is to momentum what work is to energy. Okay, so I want to talk about why this is true. Okay, if we took the sneaky form of Newton's second law, okay, net force is change in momentum over change in time. All right, and we multiply both sides by delta T. What we get is that the net force times delta T is equal to delta P. Okay, but this force times time is the definition of impulse. So, and this is kind of an important point. The impulse due to the net force is equal to the change in momentum of the object. Okay? Not just one of the forces, but the impulse due to all the forces combined is the change in momentum. Okay? I should have made that distinction a little bit clearer when I lectured on work as well, because it's also true of work. The work due to the net force is the change in energy. All right, so let's do a little example that illustrates this this relationship right here, and then I will be done. So let's suppose that we have a 3 kilogram particle has initial velocity equal to -5 meters per second. Okay, so it's going to the left. It experiences this force time graph. The force time graph that I'm about to draw. Force in newtons, time in seconds. There's 0, and it looks like this. So the peak force is 10 newtons. This is 2 seconds, and this is 3 seconds. Okay? So let's go ahead and calculate the area under the curve so we can get the impulse. I'm going to think about this as a 2 by 10 rectangle. Okay, and then I have a 1 by 10 triangle. So this is going to be 1/2 times 1 times 10. That's going to be the area of that one. Okay, so and by the way, this is the net force. Okay, so the net impulse is going to be 2 times 10 plus 1/2 times 1 times 10. So that's 20 plus 5, 25 Newton seconds is the impulse. Okay, we can use that to figure out the final velocity of the particle. Okay, so the impulse is equal to the change in momentum. So what we have is 25 equals final momentum, which will be 3 times v final. Remember, it's a 3 kilogram particle. Okay, so mv final minus the initial momentum, which is 3 times the velocity of -5. Keep in mind that we have a double negative here, so that becomes a positive. So we have 25 equals 3 v final plus 15. I subtract the 15 over to the other side. So we have 10 equals 3 v final. Divide both sides by 3. We get 3.3 meters per second equals v final. Okay, plus 3.3 meters per second. So it's actually, this force, because it was in the positive direction, it actually had enough to reverse the velocity of the particle from negative to positive and almost get its speed back up to the original speed. Okay? Just one last thing really briefly is on midterm 2, I will try to confuse you with the difference between work and impulse. So make sure, a really good idea would be to just keep a piece of paper with all the key facts that we're learning. Don't worry about the examples, but just the key facts, like area under a force displacement graph is work, area under a force time graph is impulse. Okay, just collect that all in one place, because I will give you a graph like one of these, and I'll say what's the final velocity, and if it's a force position graph, you're going to want to use this idea, and if it's a force time, you're going to want to use this one. Okay, so it's easy to get confused. All right, so that's my lesson for today. I hope you guys have a nice day. Bye now.